This video covers the back-end orchestrated reactive UI architecture, an implementation of the architecture foundation, A1R. The diagram illustrates the reactive flow, showing how data streams and events connect different modules, including the back-end orchestrator and the user-facing components. A formal tag registry is essential for reactive systems. Tags like component role determine state authority, state persistence defines memory handling and checkpointing, and security classification restricts network visibility and enforces encryption. The architecture ensures product-to-stakeholder alignment. Executives focus on system stability, while developers handle implementation specs like API contracts. Operators are concerned with telemetry and node execution, ensuring the system runs smoothly. A key function is bridging logical to physical. The multi-agent orchestrator manages logical interactions and state transitions. This then maps to the physical execution, resulting in DOM updates in the browser runtime environment for the user interface. Agent caging and the thin client implement core architectural principles. The state graph acts as a gatekeeper, intercepting autonomous actions to validate NAF compliance before rendering to the passive thin client. The backend remains the single source of truth. The component maturity registry tracks the status of different components. For example, reactive streaming prototype is the baseline, dynamic path highlighting is currently a draft, and procedural fast API routing is retired. The architecture has evolved from a V1 legacy model, which had a high risk of state desync, to a V2.0 event-driven reactive pattern. This current version enforces absolute server state authority, ensuring the client only renders streamed state events. The master traceability index ensures absolute traceability for every reactive UI component. L3 maps to semantic query and orchestrator flow, while P6 maps to hardware-level data exchange, preventing orphaned UI elements. Implementation and security standards are critical. Implementation standards include LangGraph's @stream API and server-sent events for real-time updates. Security protocols involve TLS 1.3 for transport layer security and AES 256 for state encryption. The phased implementation roadmap moves through 3 phases. Phase 1, data-driven refactoring, is complete. Phase 2, visualization decoupling, is in progress. And Phase 3, full state machine orchestration, is the target phase. The reactive governed enterprise is achieved through methodology as code. By centralizing state on the backend and caging autonomous logic, the architecture guarantees methodological compliance without compromising real-time reactive user experiences. Here is some other implications of applying graph state machines and the projects we have planned out for them. The A1AR diagnostic framework applies standardized methodological lenses to all orchestration architectures. It includes metadata, architectural products, correspondence, methodology, status inversions, standards, and the roadmap. Architecture 1 focuses on subgraphs, ensuring decoupled execution environments through shared state keys and state isolation. The primary stakeholder is the developer, supporting team scaling and functional isolation. Governance for subgraphs includes standards for data contracts and a roadmap. This roadmap phases from monolithic unbundling to fully decoupled parallel team deployment. Architecture 2 is the graph factory, which uses factory metaprogramming to create deterministic configurations and topology outputs. Correspondence is handled by dynamic generation using JSON declarative rules. Governance for the Graph Factory emphasizes standards and security through sandboxing, abstract syntax tree manipulation, and a critical prohibition of raw eval vulnerabilities during dynamic instantiation. Architecture 3 introduces hybrid graphs, utilizing agent caging. This methodology bounds probabilistic LLMs within deterministic software guardrails, guaranteeing 100% predictability in execution routing. Governance for hybrid graphs sets standards for data access and AI inference constraints. The roadmap details a phased transition to fully autonomous, validated hybrid operations, including human-in-the-loop interrupts. Architecture 4 is backend orchestrated UI, where the backend dictates the state and the UI acts as a passive renderer. The methodology ensures a single source of truth, creating reactive views for the executive or product lead. Governance for backend orchestrated UI defines standards using strict protocols like SSE and WebSockets. Status and versions include UI state versioning for time travel debugging and user session recovery. Architecture 5, Recursive State ORM, uses an in-memory graph DB. Execution relies on recursive tree traversal and channel synchronization. Correspondence links logical context chunks to physical face or SQL storage. Governance for Recursive State ORM enforces standards for persistent CRUD operations. The roadmap progresses from flat memory dictionaries to deeply nested object relational graphs. Architecture 6 explores self-optimizing compilers. This methodology uses self-evolving states for safely hot reloading code and dynamically morphing schemas at runtime. The process involves analysis, generation, migration, and reload. Governance for self-optimizing compilers utilizes runtime metaprogramming standards. Critical checkpoint invalidation is prevented during schema migrations, moving towards a fully organic, data-morphed architecture. The cross-architecture synthesis demonstrates a progression from isolated development with subgraphs to fully autonomous software adaptation with self-optimizing compilers, ensuring safety through deterministic control. We're already building up a palette of user interfaces which stream these state machines over WebSockets to provide synced sessions using the LangGraph memory checkpointer. Each session is bound to a unique thread ID, so if we wanted a unique session that's not a shared work environment, that's easily configurable. The vision for this project is to encapsulate every HTML element for enforced control over the DOM and tracing through the Langsmith API. We can even use this to revert changes to the state using the time travel feature, which our next project demonstrates perfectly. Here we are using the LangGraph state machines to encapsulate Python abstract syntax tree nodes. When this project is finished, we will be able to perform automated deterministic refactors and generate usable Python code through scripts which enforce architectural constraints. We can see our code at 5 levels of granularity: the full AST, which shows all the details, the expression level, which describes the different parts of assignments and function calls, the statement level, which describes each line of code, the structural level, which describes class and function definitions and other logic that exists globally, and the architectural level, which shows relationships to other files and the code within them. Here's some practical applications while I work through the demonstration. Python fast API servers have a neat automatic reloading feature, such that when you update an imported file dependency, it automatically reloads the server without needing to restart it. As long as you don't modify the actual script which is running the server, you can update without ever having to turn it off and on again, which could compromise your session states and database syncs. By using the automated code builder to enforce architectural requirements, we can ensure that there will never be any breaking changes to the production environment, even when we add or replace code. All we need to do to make this happen is import both the development and production versions of our files into the server from the start, and use a conditional edge on our graph so that our development node fails, we can fall back to a previous version until the feature is stable. If any actual damage would be done to real data, we can use the time travel feature to roll back the changes to state and automatically update our databases. By organizing each graph to be configured with a unique checkpoint or thread configuration, we are able to trace all of our activity over on Langsmith to see exactly what broke and where. Some other benefits to this architecture is that we have virtually removed the need for front-end JavaScript altogether, and we're able to easily generate HTML and CSS to structure a web page using Python. Since everything is controlled through the Python backend, we can now apply classes and functions to previously static elements. HTML is finally a programming language. I don't know about you, but I will not miss having to debug the front-end JavaScript, CSS, and HTML every time something changes in the administrative, structural back-end data or computation layers of my infrastructure. Now we can effectively deduplicate that code into a single Python file and reuse common structures similar to React components without the headaches, security vulnerabilities, or the black box of your node modules folder. This is especially important if you're using AI to write code. I guarantee you're going to burn through your quota immediately if it decides to read your node modules folder all at once.
Let's stick with Python and automate security policies and best practices. Now ask yourself this: why doesn't your AI coding agent have tools to perform this granular AST analysis? That's exactly what it needs to ensure high code quality. There's just one problem. The best code can be generated entirely deterministically through AST manipulation. This project is designed to do just that. We're going to automatically refactor all of our code into specific directories and catalog each and every level of granularity with verbose descriptions into a custom nested data structure, where every level has find, filter, and contains methods to make your automatically organized libraries into queryable code snippets. If we give the AI the ability to manipulate the AST, all it will ever need to do is change specific values. And if it makes a mistake, our deterministic architecture suite will automatically course correct. So what's left for AI to do now that we've automated its job? It seems to me that the best use of AI is to test declarative statements and force it to provide Boolean outputs for the procedural tasks, or to write out descriptions and other filler content that makes things easily queryable. You can't compute if an image contains perfectly centered documents acceptable by a bank for your loan.
Let me know if you're interested in working on any of these projects in the comments below. I'd love the feedback. Some quick questions for the audience. Gemini CLI is being paywalled in just a few weeks. What's the best alternative available? Are there any libraries or tutorials for using the Red Baron Python package to manipulate Python AST? Like and subscribe for more DevOps tool demonstrations. Roll credits.